This is the Chapter 4 lecture on data analysis for experimental design. One of the principles we need to start with is the concept of mean and variance. In your math classes, you would have already talked about some of these concepts, and we mentioned the idea of the arithmetic mean and the standard deviation last week in the last chapter, in Chapter 3. So when we talk about mean and variance from a statistical standpoint, we're looking at how to describe statistics, specifically a probability distribution. And the mean would be the center or the middle. So just like the arithmetic average sums up all of the given values and divides it by the number of values, a mean for a probability distribution sums up all the values of X with relationship to their given function. The variance is looking at dispersion or the variability within that distribution. So how far away is each of those values from the mean? This is the same calculation we would have seen in Chapter 3, looking at standard deviation, just constructed in terms of f of x and the mean, mu, because we're looking at a distribution rather than just a single set of numbers. A normal distribution has a bell-shaped curve and is useful in describing data because we can say that one standard deviation away from the mean, either above or below, so plus or minus one standard deviation from the mean, covers 68% of the data under the curve. Two standard deviations away from the mean, plus or minus two standard deviations, covers 95% of the data under the curve. Three standard deviations, or plus or minus three standard deviations away from the mean, covers 99.7% of the data under the curve. These calculations are very helpful when we're trying to predict information. When we know that data is normally distributed, which we can test for using statistical measures, then we can actually predict their responses given a mean and a standard deviation. Now, the binomial distribution is a special case that has a set probability where we know that the probability of occurrence can only be two outcomes, either true or false, yes or no. It's only one or the other. Now that probability of occurrence is noted as P, and the number of trials that are taking place in a given experiment is noted as N. So the mean of a binomial experiment is simply multiplying N by P. And it really is as easy as it sounds. As you see in this example, if you have 4 trials and you have a probability of occurrence of 0.1, then the mean for this binomial function is 4 times 0.1 or 0.4. What's helpful is when we understand that these two states of success or failure, it's very helpful in engineering functions. So think about most manufacturing tests to see if something meets quality standards. It's a pass or fail test. Or think of a circuit that is open or closed circuit, or think about turning a light switch on. It's on or off. Now, a dimmer switch would be a different type of variable, but a binomial random variable only has those two states, success or failure. And so we can actually create that same type of bell curve that we saw for a normal distribution in a binomial distribution as well. Now, this probability mass function is given to you in this bottom equation, the f of x, and it uses a combination math that you would have seen probably in Calculus 1, where we can see that we look at the probability of occurrence in a certain number of trials, and we know the probability of success, and the failure would be 1 minus the probability of success. And so you see in this graph here that the probability mass function for a binomial looks very much like a normal distribution. It looks like that bell curve. And so depending on how large your n is and where your probability of success is, the shape of your curve will change. So if you look at the red dots, for example, your probability of success is 50%. It's a 50-50 shot. and your number of trials is 40. And so N times P, or 40 times 0.5, means that our mean is at 20. And you see that the top of this curve indeed is at 20. And it has that bell-shaped curve the rest of the way. Now, in the case where N is only 20 and P is 0.5, you can see that even though it has the same probability of success, with only half as many trials, we have an expected value or a center point of 10. So that's our mean, but the curve is shaped a little differently. The curve is a little taller and a little steeper on the sides. This tells us that we need more trials to get closer to that normal probability shape. And that's what we learn in statistics as well. So even if you haven't taken engineering statistics, it's easy to remember that when you have a larger number of trials, and traditionally they actually say 40 or more, when you have a larger number of trials, that your binomial distribution looks like a normal distribution, just like we see here. And so when we talk about data analysis and our collection of data and our statistical analysis of data, typically as engineers, we're not just going to include raw data. We're going to translate it into some sort of meaningful communication, and usually that's done graphically. But we have to keep in mind who we're talking to and what we're trying to say. So for example, in this chart, we have a pie chart that shows the percentage of time millennials watch movies or television shows on various devices. The table on the side is showing the same data that the pie chart shows, which just helps us to see that data can be presented in a variety of ways. The pie chart is more colorful, and that visual can actually help show that even if you didn't have the numbers there, you would know that the television set is still a very, very large category, with the next largest category being a laptop or desktop. You would see a much smaller sliver for the smartphone or tablet. Now, what's interesting about this is that if you were looking at maybe the I generation or Gen Z, you would probably see a lot smaller quantity on the television set or a laptop or desktop, and a lot higher number on a smartphone or tablet. So this information is really useful when you're thinking generationally. For example, if I was trying to create a show and my target audience was for millennials or people older than that even, those older generations would be more likely to watch it streaming on TV. Where if I was making something aimed at younger people, I would probably want to convert it for a smartphone or tablet setting. In this graph, you see a Pareto chart, which is a chart that numbers quantities, categories from largest to smallest, and it shows a cumulative trend line. So it shows the cumulative percentage, that's the red line going across from 0 to 100%. And then it shows the individual frequencies for each of the bars going across the bottom. Now this chart you'll see is a little bit different. We don't have specific data points given for any of these. All I can do to figure out where they land is to look at the specific side categories where I can see the 20% increase, 20, 40, 60, 80, 100, and get rough estimates. That's not really helpful as you look at the small categories that are much less than 20%. The first two I can estimate pretty well, maybe 50% for the warped card, maybe 30% for the card unreadable, but all the other categories, it's very difficult for me to know what number they might be because it's such a small number compared to the axis. This is a really good example of a bad chart because I can't discern the right data from this information. So while the last chart gave me the data in two different ways, a table and a graph, and I could see visually just by looking at the colors, which ones had higher levels than the other by a really great margin. This chart, I really need to have the numbers if I'm going to understand the different levels for this chart. In this graph, you see here that we have years and number of franchises of Jimmy John's by a specific year. And so the axis going across the bottom is showing the years in ascending order, and then we see the number of franchises. I don't have a line connecting this, which isn't necessary. What I'm really looking at is a trend here. I see a peak at 107, and again, I have both the table and the chart, so that helps me to see what the exact values are, even though I can't determine the exact values from the chart alone. So it's important to keep in mind, if people need to know exact values, if you're going to provide them a chart, you want to include a data point. If you're not going to include the data points on the chart, a table is also helpful. So this shows that even though the data labels are not on the chart itself, like the previous example, the table provides all that meaningful data. In this one, I'm looking at a comparison of success and failure. I don't have data labels on the chart, but I do have order of magnitude. The two different colors, not successful being orange and successful being blue, are good contrasting colors. And while I don't know the exact values, I can see a large difference between the success and failures, and I can see a large difference between the different categories. This chart is showing things side by side, which can be helpful when you're doing a comparison like this. You can also do bar charts that are oriented vertically instead of horizontally. It kind of depends on how you want to create your bar chart as what is more helpful. Data labels could be helpful if the specific values were required, but if I'm only looking at order of magnitude, in this case, the data is different enough that the order of magnitude is pretty clear. Here I'm looking at a histogram, and a histogram is a bar chart that is set up to be kind of in that bell curve shape. So I look at the midpoints for each of these bins. In histograms, you have bins, and I have percentages, which is a frequency of occurrence, which is how a histogram is created. These are looking at credit scores of adults 25 to 30. And I would really be looking at the shape of the curve here. I'd be looking at where the highest point is. Again, I don't have data labels. I don't have frequencies. I'm kind of just looking at the shape of the curve because of the limited information that I have. So as you're crafting your tables and you're crafting your charts to display data for individuals, you need to be thinking both, what am I trying to show, and what's the most important thing that this data table or graph or chart is going to display. If the shape is the most important thing, you don't necessarily need data labels. If the specific values are the most important things, a table might be enough. If you want to show order of magnitude between differences, having something like colorful charts showing differences can be very helpful, but also giving data tables or including data labels on the chart itself so that people know the exact values. A time series plot is a good thing to show over time. Again, this is too much data to have individual data labels, so I would be focused on the trend line. So when you have lots of data pushed together like this, you would not want to include data labels. You would want to just be able to show a trend, and that is how you would discuss it within the narrative of your report as well. Anytime you're presenting data in a report, you should be referencing it within the body of the report, and you should be, as you go through it, the reference within the narrative should be helping the reader understand what it is that they're looking at. So for this time series plot, you would be describing what's most meaningful about this. So for example, you might want to talk about how there was a peak in between October 2006 and July 2007, but then there was a dip in January 2009. So you would draw the reader's attention in the narrative to what you would specifically want them to view in the specific graph that you're looking at. So including your charts, graphs, figures, images in a technical writing piece is never to just put it there. It should always be included in your narrative, and your narrative description should always tell the reader what they should focus on. what's interesting about this included figure or table. Now, in this week's class, you will be doing a coin flip experiment and you will be including your own charts and graphs. And there are some best practices that I want to include here in this specific realm of data analysis. One thing that people have done in the past is they have included tables and included all of the information, raw data, including individuals' names. Now remember, in our qualitative data analysis, we are objective. We do not need to know individuals' names. It does not matter who performed the experiment. The experiment would have taken place the same way, no matter who conducted it. So you never need to include names, even when you're including raw data. This column is completely unnecessary. The other thing is that this table, as presented as it is, doesn't really give me a lot of information to know what specifically I should be looking for. Nothing is highlighted, nothing is featured. It's all presented just as raw data. I would shy away from presenting raw data unless there's something specific you want to highlight. So if multiple people have the same response, so for example, in this class, I think the author was trying to highlight how many people had 26 successes. We have 1, 2, 3, 4, 5. It's actually statistically unlikely that you would have 5 individuals with 26 successes in this experiment. It defies statistics. So that would be a reason to show this raw data. But if you were going to do that, you might want to highlight those columns to illustrate that point more clearly. Again, names are not necessary, but you might call it student 1, student 2, student 3, or experimenter 1, 2, 3, or trial 1, 2, 3. So you might number them in some way to differentiate them, but names are never necessary. In this case, somebody presented their data and they showed for each of the 14 trials the successes and failures side by side. The raw data is given below, so there's no data labels on top, which helps it from being cluttered. But again, it's not very clear what specifically I need to be focused on. Hopefully the narrative would be clear as to what was most important about this graph, because essentially they've provided me all of the raw data. The raw data itself is not necessarily interesting. Analyzing the raw data for some particular conclusion is what we would be doing as engineers. We're not just collecting data, we analyze data and make decisions about it. So looking at this data just as raw data is not necessarily helpful. One thing that could be helpful is in the coin flip experiment, our expected value would be 25 successes, because if you flip a coin 50 times, you know the probability of success is a 50% success rate. And so 50 times 0.5 is 25. You'll see in this class, person number 2 and person number 11 both got 25 successes and 25 failures. That's actually fairly unique. So this could potentially be highlighted, and they might highlight that in this table below. Or you could potentially add a line, a y equals 25, going across to show what that expected value should have been. So there's a couple different ways you could make this table and chart more interesting to the reader and do more than just present all of the raw data. This individual showed all of the data for all of the students for the entire year. And as you can see, it is completely unreadable. This is exactly how it appeared in the paper, and it is completely unreadable. Now, there is one thing that stands out on this graph, and that is this mark here where someone has 35 successes. That is, again, statistically unlikely. So if they were to remove all of this data below, so it didn't look so cluttered, and maybe remove all of the failures, but only included successes, and we could see this peak of 35. We also have one, I think this is 32, and another one of 32. So if they were showing these really wild outcomes, and removed all of this data that's completely unreadable below, this would actually be more impactful. So think about the impact your graph is having. How is the reader going to interpret that? Because we're not just presenting data to, to say that we did it. We want it to be meaningful. We want the reader to get additional information and to have a good visual understanding. This does not provide a good visual understanding because it's too busy and it's cluttered and it's confusing. But if they were to remove all of the failures and they were to remove all the data below the x-axis and just highlight the successes, this could actually be a really helpful table. This was a trend chart that was put together by a student, and I always like to show the impact of scale. You can see here that they are trying to show trials, successes, percents of successes, probability mass function, and cumulative distribution function, all on the same graph. We have values as low as 0.00286 and values as high as 4,850. Which means a lot of the data is down here at 0, and all of these lines are just on top of each other, and you can't even tell what you're looking at. This is a terrible chart because you cannot distinguish on this type of scale the difference between all of these decimal values and these very large values in the thousands. So one chart is not helpful in this case. Now, if you break these charts into multiples, so this one is looking at all of the decimal values. You see that 0.00286 here. And you have this one that's looking at the 1,000 values here. And your cumulative distribution, this is looking from 0 to 1 here. Now, each of these axes are still over those 6,000 trials, but your y-axis matches the correct values for the data that's being presented. So by breaking out those charts into 3 different charts, you're able to present the data in a meaningful way that the reader can actually understand what you're looking at. So be mindful when we are presenting data and doing analysis. We want to be aware of what the ultimate goal is. Our ultimate goal is that our technical report would be better understood by the visuals we provide. And the visuals we provide have to align with what we are saying, and they have to make sense to the reader. They should not increase confusion. They should bring clarity.